Alright, hi. Today we're going to be talking about the Hall effect. So here we have a rectangular box. It's hooked up to a power source, in this case a battery, which is attached to the left and right hand panels of this rectangular box. We have an ammeter going through that same circuit. We also have a voltmeter attached to the top and bottom panels of this rectangular box. And we have an external magnetic field that's pointing out of the screen at us. And they give us a lot of these magnitudes. They also give us some extra information, and if you're interested in the full problem statement, you can find that in the description here. But they also give us U. U is the charge mobility. In this case, that is 3 times 10 to the negative fifth meters per second over volts per meter. They also give us the charge density, that is just literally the number of charges per unit volume. And in this case, that is 7 times 10 to the 23 charges per meter cubed, or, often this is just written as per meter cubed. Okay, excellent. So there's some extra information that they give us. Now, the first question that they ask of us is the direction of the magnetic force, FB. Okay, so this is kind of what we're interested in here. Now, what I'm going to do is just redraw this rod in just 2 dimensions to kind of clarify what it is we're talking about. I'm also going to redraw the battery as just a schematic of a battery. There it is. So notice that we have the positive end of the battery attached to the left-hand side of the rod, negative end attached to the right-hand side of the rod. And so what we end up with here is actually an electric field that exists kind of between the left and right-hand sides of this rod. In this case, I'm going to just call it E parallel, since it's kind of parallel to the direction of the length of this rod. So there it is. So there's our E parallel pointing from left to right, the positive end to the negative end of this rod. Alright, now we still have our magnetic field. That's our B field that's pointing out at us. That's supposed to look like an arrow coming out of the screen pointing at you. And then we also have these positive charge carriers. Okay, they exist within here. Now, FB, you might remember, we have an equation for determining the direction of FB in conjunction with the right-hand rule. So here, we're interested in the direction of QV and B. B is out of the screen at us. Now, V, the velocity, the direction of motion for these positive charges, is going to be the direction of this E parallel. So in this case, it is just going to point in this direction. So my V is pointing to the right, my B is out of the screen. Alright, here we have the bar. We have our mobile charge carriers. These are positive charges in this case. They have a velocity to the right, and the B field, the magnetic field, is pointing out of the screen at us. Now what we want to do is figure out the direction of the force from the magnetic field on these positive charge carriers. So what we do is we look at Q times the vector V. The vector V is pointing to the right, and Q is positive, so Q times V is pointing to the right. If Q had been negative, Q times V would be pointing to the left. So Q times V is pointing to the right, so I'm going to put my 4 fingers of my right hand in the direction of Q times V. Now I want to cross it with B, which is pointing out of the screen at you. So in order to do that, I want to sweep these 4 fingers in the direction of B. And in order to do that, I need to rotate my hand like this. So Q times V is in this direction, and I can sweep them in the direction of the B field, out at you. Now I have my thumb resulting downwards. This gives us the direction of the force from the magnetic field. So this is going to be a downward acting force on these positive charge carriers. Alright, so now we can fast forward sometime later through the magic of YouTube, and we see that this magnetic force on these positive charge carriers causes all of these positive charges to collect at the bottom of this rod. Likewise, we could say that we have a deficiency of positive charges at the top of the rod, which is kind of like saying that we have negative charges collecting at the top of the rod. So now what you see is that we have a potential difference that's created across this axis of the rod. So since we have a voltage now across kind of the vertical axis of this rod, we also have an electric field. And this electric field we're going to call E perpendicular, or E transverse if you prefer. So now that we have an E field, we notice that this E field is pointing upwards because they're pointing towards these negative charges. We thus have a force, an electric force that is produced that is also upwards. The Hall effect tells us that we'll have this collection of charges occur in this way right up until the point where these two forces, the magnetic force FB and the electric force FE, are equal to each other. Okay, so here we've determined then that our magnetic field, FB, is pointing down. As you just saw in that video, that means that all of these positive charge carriers are going to aggregate at the bottom of this rod, like this, and therefore we have sort of a deficiency of positive charges, or we can think of them as negative charges, at the top of this rod. Alright, excellent. So we've already answered this question about where FB is. We've just also gotten a little bit of extra information that might help us with part B of this question. Part B asks us for the sign of the voltmeter. Sign of the voltmeter. So in this case, you'll notice that the voltmeter is attached, again, to the top and bottom panels, where the positive end of the voltmeter is attached to the top panel. So the voltmeter would read positive if this top panel was more positive in relation to the negative, or to the bottom panel here. But what we see, as you just saw in this picture here, is we see that the negative charges are aggregating on top. So the lower voltage will be at the top of this, or the lower potential difference will be here at the top, which means that the negative end of the rectangle is attached to the positive end of the voltmeter, and therefore we can say then that the sign of the voltmeter will be negative. Okay, excellent. So that was actually really quite helpful. And another way that we could think about this, if you prefer, so we can sort of, let me just draw here another picture for us. We have that this FB is pointing down like this. And what we're seeing here is because these positive charges are on the bottom, negative charges on top, we're actually creating a new electric field. And that electric field is pointing up, again, from positive to negative, and in this case I'm going to call it E transverse or E perpendicular. And so what we have then is a force that is exerted due to this electric field, this E transverse, that is upward. And this is F sub E in this case. Okay, what we also saw in the video is that the two magnitudes of these two forces have to equal each other. Okay, so this is going to come in handy for part C of this problem. In part C of the problem, we're looking for the magnitude of the voltmeter reading. Okay, so in other words, we're looking for the magnitude of the potential difference between the top and bottom surfaces here. Okay, so let me just scroll up here a little bit so that we have some more space to play with things. Okay, so what we just said a moment ago is that Fe, the electric field, the magnitude of the electric field, has to equal the magnitude of the magnetic field. Okay, we write Fe here as QE, where E is the field that is causing it, so in this case it is going to be this E perpendicular. And FB we've already written before. We wrote that as QV cross B. I'll write that in terms of just its magnitude, so QVB sine theta in this case. Theta is the angle between the two vectors in that cross product. So in this case, the angle between V and B. V is to the right, as we saw in our previous picture. B is out of the screen at us. That means that there's 90 degrees between the two of them. Sine of 90 is 1, so that crosses right out. We have Q's in both of these, so those drop right out. And then we're just simply left with the fact that E transverse is V times B. Okay, now we're going to need the magnitude of E transverse if we're trying to figure out the potential difference between the top and bottom segments of this rectangle. So we're trying to figure out E transverse. We know what B is, we don't know what V is. Okay, so let's work a little bit harder here to figure out what that drift velocity is. So maybe off to the side here, we'll do a separate calculation for the drift velocity, V. Okay. Now, you may remember that the drift velocity V is just going to equal the charge mobility, U, times the magnitude of the electric field that's sort of causing those charges to move, in this case from left to right. So that was what we were calling E parallel. Notice that we have these two different electric fields here, so we're trying to keep those straight. So here it is, this is what we have. Now, E parallel, so I'm just going to carry that U over, E parallel is just simply the delta V, again from left to right here, over the length. Okay, and again, this is kind of from left to right, sort of along the x-axis. I'm going to call that L sub x here. Okay, so this potential difference is caused just simply by this battery here of 1.2 volts. So now I can just very easily plug everything in here. And if I do that, so if let's see here, I've got 3 times 10 to the negative 5 times 1.2, again that's in volts, divided by, we said that the length of this rectangle is 11 centimeters, so that's 0.11. What we end up getting for this drift velocity is 3.27 times 10 to the negative 4 meters per second. Okay, great. So now we found this V. We can go ahead and plug this in to this V here. We know what our B is, and therefore we can figure out what our E perpendicular is. Okay, great. So in fact, before I even do that, let me just move on then to the next step of this process here. So we're trying to find the voltage difference between top and bottom here. Okay, so let's recall, we're going to use essentially the same equation that we just used here a moment ago, that E is equal to delta V over L, but we're going to now use it between the top and bottom segments of this rectangle. So our delta V in this case is going to be E, in this case the transverse component of E here, times the length, this time in this Y direction. Again, I'm looking for that potential difference in this case. So now I have, so my delta V here is going to be VB, just coming from here, that E transverse is V times B, times LY. And I can literally just plug everything in at this point. So my V is 3.27 times 10 to the negative 4 meters per second times the B, which is 1.8 Tesla, times the length in the Y direction, which they've drawn in as 3 centimeters, so I'll write that as 0.03 meters. And what I end up getting in this case is that my delta V, just plugging everything in, is 1.8 times 10 to the negative 5 volts. Okay, excellent. Now, if you're interested, we can also talk about what the ammeter will read. Okay, so the ammeter, so this will be kind of our part D of this problem. So, ammeter. In other words, we're looking for the current that is going through this top loop of wire here, this one where the battery is attached. Now, there's a couple different approaches that you can take. I think that the easiest one is just saying that the current I is N, the charge density, times Q, whatever our charge is, times the cross-sectional area of the thing that it's traveling through, times V. Okay, where again, V is this thing, this drift velocity that we've already found right here. This 3.27 times 10 to the negative 4, yada, yada, yada. Okay, so that's going to go in here. Now, the area is a little bit tricky. Which area do we use? We're going to use the area of this, the cross-sectional area of this rectangle. So this is going to be kind of the area in the YZ direction, if you prefer. So this is going to be NQ, L, in the Y direction, L in the Z direction, times our drift velocity. And if you plug everything in that's given to you, you should get 0.022 amps. There is another way of doing this where you can use instead Ohm's law in conjunction with the fact that you know that your R is just going to be L over sigma A. And your sigma, that's your resistivity, that's Q and U. And actually, if you plug everything in, you'll find out that you get essentially the exact same equation that we had just a moment ago here. So that's it. You'll end up getting the same result. I hope that you enjoyed this exploration of the Hall effect.